everyone, this is our lesson on half-life, fission, and fusion. So by the end of this lesson, you should be able to explain the process of radioactive decay, specifically with half-life now. So let's talk about what half-life is. This is the amount of time needed for half of a radioisotope to decay. So we're specifically looking at radioactive material, and we're looking at however much you start with, the time it takes to break that down to half of your original amount. This is specific to each isotope. So, like if you have multiple radioisotopes for the same element, each of those isotopes will be different in terms of their half-life. This is also independent of sample size. So the amount of time it takes for 50 grams to decay down to 25 is the same amount of time it would take the exact same material to decay from 25 to 12.5. So we have some formulas to look at here. The first one is the arrow method. This is the one I tend to teach starting off because it's just easier. People can visualize the half-lives occurring. And you can use this for small numbers of half-lives because you don't want to do this if you go through like 20 of them. And all you do here is you take the original, you draw an arrow. Here, I'm going to do this. So you take the original, you're going to divide by 2. And divide by 2 again. Divide by 2 again. And so on and so forth until you have done the amount of half-lives that you need. And then the calculation, you use this for a large number of half-lives or decimal half-lives. So let's say you go through 1.5 half-lives. You can't really do the math there as easily, so you're going to want to use the calculation. And this calculation is very easy. So this A sub T, this is your new amount. Ooh, sorry, that's sloppy. A sub 0 is your original amount. And then N is your number of half-lives. Sorry, my computer's not wanting to work with me right now. So this just shows as half-lives pass, you're turning from blue atoms into red atoms because you're decaying. And this again just shows, and I don't like the way this is set up because T over H. I just like to use N for number of half-lives. It's easier. So let's try this example problem and see how we go. An isotope has a half-life of 6 hours. What percentage will be left after 24 hours? So we've got a half-life of 6 hours. We want to know percentage left, and we also know we've gone through 24 hours. So we have underlined and well, we did. Where it all went. There we go. Stop. My computer is not wanting to work. Sorry, it's kind of freaking out on me for no reason. So we've got this, and we also know that since it says percentage, that means we're starting out with 100%. So your A naught is going to be 100%. So looking here, time passed, you take that and you divide it by the half-life to give you the number of half-lives you've gone through. So 24 divided by 6 tells me we've gone through 4 half-lives. Not bad. And then the percentage means that our original amount is going to be 100%. So you can do this with your arrow method and divide by 2 each time. So we've got to do it 4 times. So 100 divided by 2 is 50. That's 1 half-life. Divided by 2 is 25. That's 2 half-lives. Divided by 2 is 12.5. That's 3 half-lives. Divided by 2 is 6.25. That's 4 half-lives. So you can do the arrow method here, or you could do the calculation. So 100 times 1/2 to the 4th is equal to 6.25. Something very important to state here. This part, the exponent part, do this first. Always do the 1/2 to the exponent first. So you go ahead, let me move this back. You go ahead and try this example, which is in your notes. So fluorine 21 has a half-life of 5 seconds. How much of the sample did you start with if after 63 seconds you had 25 grams of F21 left? So you actually are looking for the A naught, not the AT. Okay, so go ahead and try that one. Pause the video and try it because it might take you a minute. Now let's discuss fission and fusion. So fission means break apart. So we're breaking into smaller things. And this is when a radioisotope is bombarded by neutrons. Got a tickle in my throat, sorry. So it's bombarded by neutrons to break into smaller, stable atoms. Oh, excuse me. This actually gives off a huge amount of energy. And this is what we use in power plants to make our huge amounts of energy that we use. And we do this through what are called chain reactions. So you have really, really large radioisotopes bombarded by neutrons. They break down into smaller isotopes. Usually one of them is stable, one of them is radioactive. That one gets hit with neutrons, breaks down, and so on and so forth until you produce stable atoms only. And this is also what's used in atomic bombs. So here's an example of a fission reaction. So you've got uranium 235. You hit it with neutrons, and it's going to break down into krypton and barium and give off 3 neutrons. And then the barium is the one that will keep breaking down when hit with more neutrons. And this picture just shows you what happens in a fission reaction. So it's hit with a neutron, it breaks up, and gives off neutrons to then continue the process. And fusion is where things come together. So this is the opposite of fission. This is where 2 small isotopes will combine to make a larger stable isotope. This is a form of clean energy because you're using much smaller particles. This is not cost effective though. The amount of energy you have to put in to make this happen does not justify the amount that you get out. So fission, you put a little bit of energy in, you get a ton out. Here you've got to put a lot in and you don't really get much more out. This also takes place on the sun. If we could get fusion reactors to work and be cost effective, this would be a wonderful energy option compared to fission reactions. And here's an example. So 2 different hydrogens. So you've got hydrogen and tritium, which is an isotope of hydrogen. They'll combine together to form helium, which we know is very stable. And let me get rid of this. So you can see this exact, with deuterium. And they combine and they formed a helium. They released a neutron. All right, guys, so this was very quick. We're going to focus on the